All right, so let's talk about this is sort of a the final slope problem in the worksheet. So this is sort of where whoever wrote this, probably Mr. Rose, I don't know, might have been Shola, or maybe Forbes for all I know, but whoever wrote this sort of pulled out all the stops to make this sort of the challenge mode problem. So we got a block on a slope as before. The block is moving. We have kinetic friction. We'll go into difference between static and kinetic friction later. We don't need to worry about the fact that it's kinetic right now. We just know there's friction, so you can ignore that crap about kinetic right there. In fact, I'm just going to delete it because it offends me to have it there. There we go. So we have friction, and we got this force acting. This is all on a slope. It is not accelerating. Acceleration is 0, constant velocity going up this hill. Okay, so now let's go and draw our diagram. Again, whoops. Well, let's see if we can move that to a slightly more friendly place. There we go. All right, let's draw our diagram. So once again, we have our slope. Come on. All right, slopey slope slope. There's the slope. Actually, you know what? I'm going to draw this a little lower down. I've been using up like a lot of space on the right, but no space on the left. So I'm going to try to economize a little bit. So there's our slope. There's our mass. Velocity constant. All right, there's a force that acts horizontally, so some force, somebody's pushing it horizontally. There is friction. All right, so that's basically our problem diagram. So what are the forces acting on this thing? Well, I'm going to draw the forces let's see, I'm going to use red for forces. Okay, so we've got this force here is F. That's the one that's shown in the diagram. We've got the weight, it was mass times gravity. We've got the friction force. Actually, we've got the normal force first. Pushes up on like that. We've got the friction force there. And I think that's about it. That's all the forces I can think of, right? Normal, covered the surface, normal and friction. We got this force here. We got weight. So that's it. There's no tension or anything, nothing pulling on it. So, yep, that's it. Friction force is going to act this way. Friction force acts downhill because it is moving uphill. We were told that. Okay, so, well, that was pretty easy. So let's go ahead and draw our free body diagram now and show the forces acting on this and where they are. First, we do want to set up a coordinate frame. So again, we're going to use slope coordinates. You know, it's really up to you which one's easier, which one you think is easier, but here it's sort of 2 and 2. So, and it's going to be moving this way. So really, it's in this case, it's going to be easier to use slope coordinates. So, let's do a free body diagram for the block. I like to always include, the name of what I'm doing the FBD of, even if it's semi-obvious. It's a good habit to be in, because sometimes you'll have problems where you have to do multiple free body diagrams, okay? So, there's our Y. There is our X. And the angle these make with, horizontal and vertical is theta, okay? So, now here is our point representing this block. So we've got the normal force like that. We've got weight, it's mass times gravity like that, theta, okay? We've got the friction force acting there, downhill, and then we've got this force coming in. Oh wait, hold on, my bad. It's gotta be a pull, And this force, which is acting horizontally to the left. And again, actually let me see if I can, okay. So that force, and this is going to make an angle theta there. That's a little small, but you get the idea. I should have put the F somewhere else. And there are forces, okay? Second diagram, component resolution, all right. Normal. Friction force. Okay. So weight we're going to resolve into two components. This is mg cosine theta. And here, second component is mg going this way sine theta. So mg sine theta there. And then we got this force, which we also resolve into two components. So we're going to do f cosine theta. And yeah, it's about 2 o'clock, so right above my room, the Elephant Circus is starting up. I don't know what the hell they do up there, but mid-afternoon every day, it's like this I don't know, parade going through there or something. So anyway, the other component of f is this f sine theta, which acts downward. So there we go, and this slightly, not terribly pretty looking, but it's clear where everything's going, right? And that's the point of a good free body diagram, is it should be clear what's pointing where. So let's move on down to where am I going now? So let's do our equations of motion. So let's do them in components. Sum of forces in the x direction, okay, which is going to equal, so here's our x-axis this way. To the right, we've got force of friction. We've got mg sine theta. And then going the other way, we've got f cosine theta minus f cosine theta. And well, that's all, right? So is it accelerating? No. In fact, it's not. It's got a constant velocity in one axis, and it's not moving at all along the y. So in neither case is it accelerating, so we just say it's 0. Okay? Sum of forces in the y direction. Well, I got the normal force up. You've got minus mg cosine theta going down, and then you've got minus f sine theta, because f sine theta is going down, and that also equals 0. Boom, boom. Put a bow on it, send it to grandma, because it's done. And that is what I'm going to do for that. I might come back and do one more even trickier example later on, but yeah, there you go. That should help you.